Assalamualaikum warahmatullahi wabarakatuh. We are from Group 6, and in this video, we would like to present to you our paper, which is titled pH Monitor Using IoT. And here are our members, starting off with me. My name is Rafly Rachman, and my partner, Muhammad Revansyah. In this presentation, we will break it down into four chapters. Beginning with chapter 1, which consists of the background, uh, uh, basically the opener of the presentation, and then chapter 2, which is the basic explanation, basic theory, and then chapter 3, which will include the main part of the presentation, and ending off with chapter 4 with conclusions and suggestions. Let's begin with chapter 1, which has background problems and writing objective. In background problems, in the world of fisheries, water pH is an important aspect. When introduced to an obstacle such as human error, for example, when a manager forgets or is lazy to check up, it can lead to further problems. This is where the wonders of technology come in, where we can build a system that can convey water pH data to managers. One such method to implement technology to this is through the use of Internet of Things. We will now get into writing objective. Through PowerPoint, we have created a presentable format based off of our ISAS paper titled Development of an IoT based on controlling and monitoring pH water using MQTT protocols. The paper discusses about developing an IoT system used to control and monitor water pH levels using MQTT protocols, the general components of said system, and how it will work if implemented. Let's get into chapter 2, basic theory. Starting off in chapter 2, we will explain what is the basic definition of IoT. IoT, or Internet of Things, describes the network of physical objects, things that are embedded with sensors, software, and other technologies for the purpose of connecting and exchanging data with other devices and systems over the internet. Devices like household objects to industrial tools have an IoT that lets them communicate with each other. IoT will be what is used as an application that requires a protocol to carry out data transmission, which functions as data transportation from sensors to users in a network. The MQTT protocol, which is what we'll be using alongside with the IoT. The message queuing telemetry transport is a machine-to-machine data communication protocol that resides at the application layer. MQTT sends out data that are as small as 2 bytes so that it can work in resource-limited environments such as small bandwidth and limited power resources. This protocol uses something called a publish and subscribe method, which is a pattern of exchanging messages in network communication where the sender of data is called a publisher and the recipient of data is called a subscriber. And then, closing off chapter 2, we have general components. In this IoT system that we will be creating, it will consist of 3 main components. There will be sensor nodes, servers, and subscribers. Now, our sensor nodes, this is a device that will basically act as a data collector from objects and then publishes said data to the server. These nodes have a pH probe sensor connected to a microcomputer. The second thing is servers. They will act as sort of intermediaries between data objects and the users. They will include the MQTT protocol, the broker system, PubSub middleware, and the MongoDB system running on a microcomputer. And last but not least, we have the subscribers. Basically, the users that will request to subscribe from what has been obtained by the sensor nodes. They will get them from the servers that has been stored. They not only get real-time data, but can also request data from the middleware timekeeping features.
Hello, I am Muhammad Revansyah. Now it's my turn that I would like to share the next material or content inside the chapter 3 to you all. First of all, I will start the presentation from sensor node design, server blocker design, subscriber system design, MongoDB design, and the last is performance testing results. Sensor node design. Our sensor node will function as a publisher component that retrieves pH data that will be sent to the user. This component can work with a configuration that is embedded into an Arduino. The sensor node consists of a pH probe meter sensor that is directly connected to the sensor Arduino Wemos D1 microcomputer. Beside this text, there is an illustration of how the system works using a flowchart in order to make it easy to understand. On the next is server broker design. There are multiple stages in designing a server broker middleware. But firstly, we must know the hardware and software used to create a fully working design. On server broker middleware, the hardware design uses a Raspberry Pi 2 Model B microcomputer component, while software design using operating system Raspbian Jessie, Mosquito Broker, Python language, and MongoDB system. The first step would be to get Mosquito and PubSub middleware active. These two are the bridge between the sensor nodes and the subscribers to get a flow of data. The first stage, server broker real-time. The broker server that performs the activity reception of data from sensor in real time. Real-time here is meant data reception publisher from the sensor that is directly forward to subscriber. The purpose of this feature is to make it easier for the user to monitor pH conditions, water outside the specified time. In this picture, we can see that the process starts from request connect authorization from sensor node to a microcomputer, namely a broker, and if failed or success, the broker will provide real-time data results by topic and data type being adjacent. And of course, it is the same as the sensor node that the subscriber user must validate the authorizations and identification of brokers so that brokers can distribute real-time data result to a correct user. The next stage is several brokers subscribe middleware to database. In this stage, the server brokers performs data storage activities from sensor with the sub-middleware feature to the database. The purpose of this feature is to make easier for the user to save data from the sensor so that later it can be used as a reference if something happens. This carried out by sub-middleware which stores a data from the sensor with the topic and a specified time. Then the data that has been obtained by sub-middleware will insert data into MongoDB as the database used. The next stage is server broker pub middleware daily and history. In these two stages, a feature in which the user could retrieve data on a frequency basis, for example, daily, and then a feature where the user can get a record of when each data was sent by the sensor. In this feature, the pub middleware tool performs data retrieve from a database with data limits that can be retrieved. Pub middleware does a collection find .short .limit, which means only retrieve data from time and certain data limits. In pub middleware history, retrieve data from the database uses collection.find, where the comment or the statement retrieves all unlimited data in the databases, and then publish. Users can view or monitor the results of data retrieved from sensor nodes. User will see live data in the form of real-time from the publisher. See the data that has been designed to be stored at two times, namely morning and evening. And the user can see the results of the whole data in elapsed time or history. Because these features retrieve data from database that have been subscribed to sub middleware. The next is subscriber system design. The system where the user can request data retrieved by the sensor nodes. The subscribers receive live data along with the one stored twice a day, and they can see the results in elapsed time or history. MongoDB design. The document-based MongoDB will be used for this system, and it is adjusted to support JSON files. Performance testing results. Final testing will be done in two parts. One will test the performance of the protocol, and the other will test the distance coverage area. Both results of the performance will be configured at a magnitude delay of 3.24 hours. The test is done 2 times during the course of a day and night. In the daytime latency, tests obtain the more sensor node devices used. Then the value obtained is higher, unlike the night test, where the latency obtained has the same two values on the number of devices, 100 and 200, is 0.12 millisecond, but not on much higher 300 devices, with the value of error rate the same is 0%. Area coverage test. This test is to see latency values in different coverage areas from the actual location. Instances of 5 meters, 10 meters, and 15 meters are used in each test during a period of 24 hours per instance to gather the average delay in milliseconds. From the two test results on the coverage area for the needs of the system that can be made conclude that the change in distance and weather changes affect the process that data exchange that occurs between the client and the servers on the system itself.
Closing it off with chapter 4, which will include our group's conclusions and suggestions. With the conclusions, we were able to take away that from the IoT system built, we were able to conclude that automating water pH data collection using an MQTT protocol is one among many advantages that the technological concept of IoT can offer. Using system-made applications, with MQTT we were able to create an optimal data reviewing system for the users with little to no latency when experiencing high numbers of publishers. And additionally, utilizing the middleware function, it has given the system the feature of being an intermediary between the users and the IoT device. And last but not least, our suggestions. And all in all, we think that using IoT as a way to sustain repetitive tasks is highly recommended for those looking to implement a smart, low-cost technology to their systems with little to no errors during operation.
Thank you very much for your great intentions. May all those we have shared be beneficial for all of us. Thank you very much.